thank you for your kind attention. We shall continue our discussions with the fax devices. This will be a second lectures on the voltage and the phase angle regulated devices. Where we have left, we will start from that point, that is actually that tap changer is feeding a highly inductive load. So, this is the recapitulation of our previous class. As the load power factor approaches unity, so that is for the resistive load, that interval for the, in case of the inductive load, it is approaching to the resistive load, alpha should be actually change from 0 to phi, and it is diminishes, and the interval for alpha 2 will be actually phi to actually till pi, and stretches over the whole half cycle for the period 0 to pi. So, that is the actually the changes. That means what happen in power in resistive kind of power factor, at unity power factor, the load alpha 1 should be equal to 0 and alpha 2 will be equal to actually alpha. So, that is the actually then the inductive load actually goes to the resistive load. Now, let us take another option if the load is purely capacitive. The resistor step changer has a purely capacitive loading. It is quite difficult to analyze, because you know that series capacitor is dangerous. They require the DIDT protection and all those things, but since there is a leakage inductance across it, so there is a series inductance already inserted. So, you can use it. Capacitor load here is assumed to be capacitor at a supply frequency only. Please note that, of course, according to the frequency, the system becomes omega L or omega C can be capacitive or negative. Highly inductive for all the harmonics, in order to actually terminate the thyristor's control with the voltage source of the both the terminal. This is the configuration. So, upper half cycle actually when of the lower thyristor will be named as A, same as the what we have done in case of the inductive one, and lower is B and upper is C and lower is D. So, what happened? With an appropriate control, providing the direct thyristor firing sequence and correct timing tap change, it is possible to operate a continuously controllable thyristor tap changer into the load to any phase angle, and you can maintain the 180-degree control. The internal control of this continuously controlled thyristors will be discussed now. This control is based on detections of the voltage and the zero crossing point of the current, because here current will lead the voltage, which determines the achievable thyristor commutations and define the control interval for the delay angle alpha 1 and alpha 2 for all possible load factors. The delay angle is usually controlled directly by a closed regulations loop to maintain the regulated voltage at a high reference value. So, this is the way actually it is been controlled. So, you got a V and you got a Vref. So, you got a PI controller. From PI controller actually error can be calculated, and this is actually the information about the zero crossing of voltage and current, and there will be a delay angle estimation of alpha and alpha 2, and accordingly actually you change the thyristors according to the load. So, these information V1 and V2, V1 and I1 will depend on the type of load you will have. So, continuous voltage control regulation, major disadvantage of the delay angle control of the thyristor step changer actually to harmonics, it injects harmonics, and for this we actually go towards this continuous angle control method. First, the fundamental component of the terminal voltage is phase shifted from the source voltage by a amount depending on the getting angle alpha 1 and the phi, the load phase angle, and the direction of the phase shift depends on the load phase angle, whether it is inductive or capacitive, it depends on it. This can lead to significant problem in transmission line application, where small arbitrary phase shift can have a serious consequence in the interconnected network. So, we have discussed in our previous class, there is a circulating current if there is a little phase angle delay. So, it leads to the phase angle delay, and thus we cannot do that. The thyristor tap changer with delay angle control is more likely to be applied as a voltage regulator in distribution system than as a more general voltage and the angular regulation in transmission system. Second drawback is the lower order harmonic actually have a quite sufficient magnitude. We have seen the harmonic spectrum in our previous discussions. Lower order harmonic can have a magnitude even small value of intertap voltages, which may be unacceptable in many utility applications. So, for this reason we have to actually get rid of these disturbances. Thus, what happened? We have to find a solution. An output harmonic filter is almost certainly required for continuously controlled thyristor tap changer applied to the utility environment. That adds to the extra cost to the system. The problem associated with the continuously controlled thyristor tap changer can be avoided with the application of the discrete level voltage control conventional electromechanical tap changer, that we will see now. With discrete level control, tap changing function can be achieved without introducing harmonic distortion or undesirable phase shift with any control complexity. So, it is just mechanical tap changer. So, it was previously connected to the n number of turns, thereafter it will be n1 number of turns, where n1 is greater than n, something like that. The choice of the power circuit is decided by performance requirement and the cost. Two possible circuit configuration can be actually observed here. So, this is the case of discrete level voltage regulator. What happen? You can have a n number of actually secondary and they have been cascaded. So, you have a different level of it, and you can bypass a particular level, or you can take the level through the magnetics, and thus you can step it or step it down. And in this case, either this actually 1 or 2 or any level is not used, and thus actually turns ratio of primary to secondary get decreased or increased according to the requirement. Conceptually, the simple step changing configuration in this scheme, each winding section is bridged with 4 bidirectional thyristor valve. So, this is the 4 bidirectional thyristor valve. You can allow current to pass through these switches, pass through these magnetics, or you can simply bypass this magnetics, you have a choice. Thus, may be inserted in the outside transmission line, the circuit either polarity or bypassed, giving angle 0 or plus minus 0 volt to this V by n number of steps. If 16 equal sections are used, so that n is 16 to give 33 capability over V volts, then THT will be considerably low. With the current rating I, then the total required thyristors will be actually, thyristor rating is V by 16 into 64. So, that is actually quite high value, that is quite actually low voltage. So, that rating of the thyristors is practically available in our existing network. So, for this reason, this kind of modular kind of solution discrete level control is quite popular compared to that what we have discussed previously. The rating, with this rating of the actual rating, voltage control range is 2V, and thus the ratio of the control VA range to the valve VA rating is only 2. The thyristor step changer, in contrast to the previously considered shunt or the reactive compensator, can either generate or absorb reactive power. Okay, so, they cannot control the real power. The reactive power supplied or absorbed from the line when it injects in phase or quadrature voltage must be absorbed or supplied by the AC system or load. Due to this reason, both series insertion and the shunt regulating transformer must fully rated to this actually the VI product of the rating. So, rating is quite high in case of the both shunt and the series solution, but here this configuration has some practical disadvantage. The circuit configuration also has some practical disadvantages. The winding must be broken into n equal section for this kind of configuration requiring steps and 4n thyristors level as used as shown in the previous figure. The major problem with this difficulty of producing a transformer with n small and isolated winding section with 2n leads coming from the winding structure. So, complexity is available with the manufacturing of such unique kind of transformer. Another disadvantage of this configuration is that lower system voltage, smaller control voltage V, the voltage per winding section becomes much lower at the minimum economic voltage applications point of power thyristors available, typically available power rating of the thyristors. So, a possible approach to solve this problem, the above practical problem by no identical winding section with winding trans increasing in a geometrical progression. That is what we have shown in the previous slide. So, it has got 1 turn, or the ratio is 1, 3 and 9, and subsequently what happened, the thyristors will be actually change. So, with the previously introduced the ternary winding, the proportionate 1:3:9, a total of 27 steps is obtained only by 12 bisectional thyristor valve of different voltage rating. So, this kind of configuration may solve the previously discussed problem. The total rating of the valve is the same as that of the previous scheme 4 VI, and also the half of the total number of valves. So, 6 out of 12 is operating at a given time, thus it reduces the conduction losses also. Thyristors of the higher voltage section are fully utilized, while those of the smallest sections may still operating below the minimum economic voltage level. The practical problem of the transformer winding are also reduced because you do not need that much of the leads to be come out from your core. The structure of the thyristor control with progressively large higher voltage increases both complexity and the cost both. The number of obtainable voltage steps here also reduced to 27. So, that is something that we have to keep in mind. The number of steps obtainable can be increased to 81. So, we have to make another section to 27, that is all. So, 1, 3, 9, 27. By extending the winding arrangement for the 4 winding section proportional to 1, 3, 9, 27. The equal and the tertiary progression type discrete level tap changes it appears that the arrangement using equal isolated winding section probably be uneconomical, except for the very high voltage application. So, previous this kind of actually splitting is been preferred. Most practical configuration for the discrete level voltage control utility application is probably the ternary progressions arrangement using 139 something like that transformer winding section that gives you 27 steps with 12 thyristors valve. That is one of the biggest advantage of the discrete level control. So, this is the case here. So, actually total circuit is shown in the phase 3. So, you can inject different kind of voltage in phase with del V. So, that can be this, that can be this, or that can be this. So, this is the beauty of the discrete level transformer with 27 steps. The thyristor control voltage regulator with 1, 3 and 9 transformer winding arrangement provides 27 discrete level steps. Similarly, the thyristor control phase angle where you have to inject the voltage in quadrature. So, we have already seen that if you want to inject a 90 degree with the phase A, we have to apply the voltage BC. So, thus this kind of arrangement gives you the quadrature phase angle in only one phase has been shown. So, this is with the A and this is the B with the C. So, with the delta it will gives you the 30 degree phase shift. A particular vector group is being chosen, it is basically D1 delta star 11 or 1. So, in this configuration we can have a same thing and where voltage will be added with the quadrature, that is BC, CA and AB with the phase voltage, that is will be the volt, and that will be the actually the phase angle regulation. You will inject the voltage in quadrature. This thyristor control phase angle regulator for 1, 3, 9 transformer winding arrangement to provide discrete level control. So, the switching converter based voltage and the phase angle regulator, let us have a comparison between these two. Series compensation discussed, synchronous voltage source is applied as a series reactive compensator to inject the controllable voltage in quadrature with the current. So, this is the principle of operation. It is shown that such compensator when appropriately supplied with the DC source or DC power can also provide compensation for the resistive drop across the line by injecting the component that is in phase with the current. Therefore, it should be possible that a converter based SVS with controllable amplitude V and the phase angle phi can be used for voltage and the current regulation. So, it can control both. So, this is the converter based regulator where in phase and the quadrature component of an assumed load current with respect to the voltage inserted in voltage regulation, quadrature boosting that we have discussed in previous class and ideal phase angle control are shown together with corresponding expressions of the real and the reactive current and the power exchange by SVS. So, this is basically the supply voltage and this is the in phase component and this is I and you add up the IC. So, this is essentially the voltage regulation. What happened then? Since you have applied a real current and the voltage, so what happened actually Vc into ICD. So, ultimately that particular component of the power will be IC V cos phi. Similarly, IC Q sin phi will be the QC and this is for the voltage regulation. Same way we have a quadrature boosting, you inject actually the current perpendicular to the Vs. So, what happens then, actually CD will come in this way and IQ will be coming this way, and thus that actually new PC compensating power, real power will be Vc into ICD, that will be I in sin phi, and similarly it will be cos phi. But in real angle control, there what you can do, you can inject basically Vc with any angle phi, and in that way you can also compensate real power as well as the active power. So, this is the ideal phase angle control, because you have to inject current into arc. So, this one is V1, this one is V2, and this one is actually phi. So, you have to inject in this way, not in this quadrature or in phase. So, how can you inject in an arc? So, this is the ideal phase angle regulator, where actually you have to find it out this phi, and from there actually there will be a calculations of psi. So, from there you actually inject this voltage as regulated by this particular power angle regulator, not exactly at phase, not exactly at quadrature. So, then expressions becomes, in this case from this phasor it is Vc into ICD should be the real power. So, it is Vc I cos psi minus phi, that should be the angle, and QC will be Vc I QC should be Vc I sin phi minus psi minus phi. Now, switching of the converter based on the SVC, what is the actually difference between the discrete component based thyristor? SVC, in contrast to the thyristor step changes, has the inherent capability to generate or absorb the reactive power. This is one of the biggest advantage of it. It must be supplied, and its DC terminal with a real power. That is one of the requirement, you require to have a power source, real power portion of the VA demand resulting from the voltage or angle regulation. Depending on the applications, voltage regulation or the phase angle control may require either unidirectional or bidirectional flow of the real power. So, that is something we require to keep in mind while designing that SVS based PAR. So, this is the case of SVS based PAR. So, this is a switching converter based regulator. In case of the unidirectional real power flow, the voltage injection at the terminal voltage injection at the AC terminal only supplies the real power. The real power could be supplied from the AC by a simply line combinated AC to DC thyristor converter. So, thus in this way the real power will go, and this will maintain the DC bus voltage, and from there this is a voltage source converter. This will compensate the requirement of this QC and the PC as desired. So, if the application require a bidirectional flow, bidirectional power flow, the AC voltage injection supplied or absorbed the real power under different operating condition, then power supply should be regenerative, capable of controlling flow of the current and out of the DC terminal of the injection converter. So, power has to be bidirectional. So, in this case we have to change some kind of topological aspect. So, what happened, the DC power supply for the voltage source type implementation of the voltage and the angle regulator fulfills same function as the excitation transformer for its more conventional counterparts employing a thyristor step changer. It should be noted that the rating of the DC power supply and the shunt and AC to DC converter is particularly are of angle regulators, appreciably lower than that of the AC excitation transformer. The internal capability of the voltage source converter to generate the reactive power is significant advantage of both voltage and the phase angle applications. This is because the system has to supply only the real power demand of the regulations, and consequently it is not burdened by the transmission of the reactive power. The corresponding voltage drop does what happen and result in the line loss if the regulator is remotely located. This is actually one of the drawback. The sufficiency of the regulator to supply reactive power is also important to avoid voltage collapse. So, that is something, it has a self healing mechanism. The action of the converter based voltage regulator to maintain the load voltage in the face of the decreasing system voltage does not result in increased reactive line current. The corresponding voltage drop, which may result in regenerative voltage collapse, that is something we require to take care of it. So, for this reason, the arrangement of the back to back voltage source converter has brought possibilities of implementation of the extremely powerful FACS controller, which multiply with multiple convertible functional capabilities. And what happened, here this converter essentially holds this DC link voltage, and thus the another converter in right hand side can do work very well. And this include the voltage regulations, phase angle control, in addition to the combined real and the reactive power and series compensation of the transmission line. So, phase angle regulator, this is called hybrid phase angle regulator. We have seen that most of the cases the voltage injected in quadrature to shift the change. Then can we do something so that we can inject in any phases and optimal compensation can be achieved. In that case, we consider a hybrid phase angle regulator. Hybrid phase angle regulator, it is a combination of maybe the one it is injecting in phase, another is injecting in quadrature or any other angle. Two or more different type of phase angle regulator to achieve the specific objective at minimum cost. For example, a mechanical tap changer type phase angle regulator may be combined with a continuously controllable first voltage source type angle change regulator. There we can use a space vector. So, that will be actually very correctly calculate that magnitude of the voltage and the phase required and inject that. So, this is the actually the mechanical version of it will be actually the mechanical tap changer type phase angle regulator. In this arrangement, the mechanical tap changer would provide the quadrature voltage injection. We know that if you wish to inject quadrature with phase A, we require to inject BC. Needed maintain the required steady state power flow. The voltage source converter of instead of the mechanical switch devices would provide superimposed dynamic phase angle control during the disturbances, and thus it is preferred. So, see that this is actually the regulating transformer, and these are the tap changer and the reversing switches, and it is an insertion transformer. So, you got a different phases. For example, this is ABC. So, this and this is AC, and this will be sensed, and similarly AC AB BCCA, and accordingly these are the taps. So, you can change the number of taps as and when it is required. So, based on that, for the example, this is the AB phase, and so it will be linked with some voltage of AB to compensate the voltage in this phase C. Similarly, you have a voltage source converter which exactly actually calculate the amount of the voltage required. So, you may require to compensate, let us say 35 degree. Then some portion will be quadrature and some portion will be your actually in phase. Instead of applying in quadrature and phase, this has a property of if it is a phase vector, it can inject in the phase steps of the two level inverter of 60 degree. So, you can make the combination of the voltage, let us say 65 degree you require to inject, that can come from the quadrature as well as by this. So, these two voltage will be added in series and will give you the desired voltage, and this converter acts very fast. For this reason, the compensation will be very accurate. So, what are the advantages of this hybrid phase angle regulator? This hybrid phase angle regulator can be highly cost effective, because one part is actually mechanical and thus you compensate the bulk power, and the power handling capability of this part of the converter, actually voltage source inverter, can be of the low power rating, and thus you can actually reduce the cost of the component. If the steady state flow power control require only the reactively large power. So, you require only to inject the quadrature power. So, transformer itself will be sufficient to do that. The above concept can be extended to the combination of the thyristor chap changer type, voltage source converter type, thyristor and the voltage source converter type angle regulator to achieve different objective. Different objective means you require to inject a particular voltage and the phase. So, that can also be achieved by this hybrid phase angle regulator. For example, the discrete level voltage regulator with an N identical transformer winding and thyristor valve arrangement can be made a simple, economically attractive, reducing the N manageable number. For this reason, we can student may actually refer to the this kind of transformer is called sense transformer. This is one of the versatile phase angle regulator. We shall give it to this sense transformer in the reference. Now, let us discuss about the enhancement of the transients by phase angle regulator. So, the capability of the phase angle regulator to maintain the maximum effective transmission angle during the first swing can also be utilized effectively to increase the transient stability limit. So, by changing delta, it enhances the power handling capability, and thus in the first swing it can increase the power flow through this transmission network. Transient stability improvement discussed is, we will be again take on the equal area criteria and we will show that how the transient stability is enhanced by the presence of PAR. And let us take the same equal area criteria and assume that both the uncompensated and the series compensated systems are subject to the same fault for the same period of time. Prior to the fault, both system transient power at an angle delta 1 and delta 2 respectively. Let us refer to the figure. So, this is the equal area criteria and uncompensated one. Delta 1 was the delay angle, and then you got a accelerating area A1, and ultimately due to that you got a deceleration area A2, and you know that actually fault required to be cleared, and let us assume that fault been cleared at del 3, and however this critical fault clearing angle is delta critical. On this other hand, with the PAR, let us assume that it is the same delta 1, we shall mark it as a delta A1, and the accelerating area is actually changed to delta A2. But here you have a range, you have actually changed to the value, and you can add sigma maybe 45 degree in this direction as well as this direction. Thus the maximum power handling capability P max will vary with a huge amount of range, and thus what happened, even though you actually clear out the fault at delta A3, you have delta critical is been shifted by this angle, that is pi plus sigma. So so this actually breakers and other system got enhanced time to actually mitigate the fault, as well as it enhances the transient stability. So let us take one by one. During the fall, the transmitted electric power becomes 0, and thus it is the cost of the accelerating area, while the mechanical input power to generate it remains the P constant, that is Pm. So this is given by this value. The sending end generator thus accelerates from the steady state value delta 1 and delta A1 in case of the presence of the PAR to delta 2 to delta A2 respectively, and when fault is cleared. The accelerating energies are represented by A1 and AA1. So, both area are essentially same, there is no difference. After fall, what happened? After clearing the fault, the transmitted electric power exceeds the mechanical power, and therefore sending end machine decelerates, and this is basically the deceleration area. That means the accumulated kinetic energy further increases until the balance between the accelerating and the decelerating energies are established energies, and it is presented by A1 and AA1 and A2 and AA2 respectively, is reached at the maximum angle of swings delta 3 and delta A3 respectively. The constant between the areas between the P versus delta curve and the constant Pm line over the interval is defined as delta 3 and delta critical and delta A3 and delta A critical. So, this is actually delta A critical. The margin of transient stability is represented by the area A margin and A margin. So, this is basically the A margin. So, this is basically A margin. You can see that this is the limit of the stability, and here this big area is A margin, which is actually quite enhanced. Thus, similarly, it can mitigate the oscillation. Transmission line power can also be applied to damp the power oscillation. We have seen in case of the series, in case of the shunt, and it is also applicable for the power angle regulator. The power oscillation damping is achieved by varying the active power flow in the line, so to counteract the accelerating and the decelerating swing of the disturbed machines or line. That is what happens when the rotationally oscillating generator oscillates at an angle delta increases, then del S del delta by del t should be greater than 0, that means you got an acceleration. Sorry. The electric power transmitted must be increased to accommodate the enhanced extra power to compensate the excess mechanical power. When generator decelerates, the angle decreases and the electric power must be decreased to balance the insufficient mechanical input power. So, this is the case. Now, this is basically the uncompensated delta, and with this damping ultimately this waveform becomes this is the compensated delta. First waveform shows the undamped and the damped oscillation of angle delta around the steady state value delta 0. The second shows the damped and the undamped oscillation of the electrical power. Since it is oscillating, so electrical power also will have a mean DC, that is P0, over it will oscillate and quite dangerous. Oscillation of the electric power P around the steady state value P0. So, this one is undamped, and when it is been damped you will have this kind of features. The third shows the variation of angle del sigma produced by the phase shifter. Gradually what you will do, you will actually change the phase of it. Generally it is start at a quadrature and accordingly will change. And generally what you can see that, so since it is actually positive, so you inject the negative phase to bring it down, and you inject the positive phase to actually bring it down the negative change in delta. So, by phase shifter, by changing the positive and the negative damping oscillation, you gradually actually by changing sigma, you gradually bring down the delay angle to the steady state value. So, thus this can deliver damp out effectively the power oscillation. Thank you for your attention. Thus we conclude our discussions of our third topic, that is the voltage and the phase angle regulator. We shall continue now the next topic, that is on UPFC and UPQC, where series and shunt and the PA are been combined into the single entity, and for this reason term universal or unified is added. We shall continue to our discussions. Thank you for your attention.